A spherical iron ball 10 centimeters in radius is coated with a layer of ice of uniform thickness that melts at the rate of 50 cubic centimeters per minute. So we say the rate at which it's melting, it's 50 cubic meters per minute. Then find the rate at which the thickness of the ice is decreasing when the thickness is 15 centimeters. So if we say this is our iron ball, let me say the inside part here is our iron ball, then the white part here is the ice that has been coated. What we have here is our iron ball with radius r, where we are told the r is equals to 10 centimeters. Then we can say the thickness of this coat of ice, we can say it's x, because we are not sure its actual thickness. So what do we do here? We can relate this to the volume of a sphere. Okay, so let's collect the data that we have first. We have our radius, which is 10 centimeters, meaning that the radius of both the iron ball and the ice is going to be capital R, which is equals to 10 plus x. Okay, 10 for the small iron ball, then x for the thickness of the ice. After that, we are told that it's decreasing, its volume is decreasing as per 50 cubic centimeters per minute. So since it's a rate, we can say dv dt is equals to, since it's decreasing, we say negative 50 cubic centimeters per minute. Alright, with this information, let's outline the formula first. We know that the volume of a sphere is equal to 4 over 3 pi r cubed. Okay, 4 over 3 pi r cubed, meaning that we can replace our r here with this one, since we want to find the volume of the whole thing. So volume of the iron ball and the ice, we have 4 over 3 pi. Our r here, the radius, will be the sum of the radius of the iron ball and the thickness, which is 10 plus x. Okay, then to the power 3. Since we have been given the rate at which the volume is decreasing, meaning here with this equation we need to find the dv. So to find dv, we differentiate it. The differentiation of v with respect to time, we have dv over dt, which is equals to 4 over 3 pi is just a constant, so it's going to be 4 over 3 pi. Here we write it. Then the differentiation of this part, we use chain rule, where we drop the power, so it will be multiplied by 3, open 10 plus x, then you subtract 1, we are going to have a 2. Then after that, we are going to multiply it by the differentiation of the inside function. Differentiation of 10 is 0. Differentiation of x with respect to time, it's giving us dx dt. Since we are looking for the rate at which the thickness is reducing, and we know that the thickness here we've labeled it as x, so we are looking for dx dt. Here we place the values. We have been told that it's melting at 50 cubic centimeters per minute, so we put negative 50 here where there is change in volume, which will be equal to 4. Then this 3 and this 3 cancels out, so it will be 4 pi multiplied by, here we have a 10 plus x to the power 2 times dx dt. We are also told that the thickness is 15 centimeters. So as it melts, it reaches the thickness of 15 centimeters. So what do? We put it in. So we have a 50, which is equals to 4 pi open 10 plus 15 squared multiplied by dx dt. Simplifying this part, we have negative 50, which is equals to 4 pi multiplied by 15 plus 10, we get it 25 squared dx dt. Making dx dt subject of formula, we have dx dt, which is equals to negative 50, then everything over 4 pi multiplied by 25 squared. Simplifying this part, we have dx dt, which is equal to 4 here, 2 here, and 2 here. We have a 25 here and a 2 here. Okay, so it will be negative 25 over 2 pi multiplied by 25 squared. This 25 and this 25 cancels out, so we have dx, so here, sorry, it's t, here also it's t, so dx dt will be equal to negative 1 over 2 times the 25 that will remain here, it would be 50 pi. This will be in centimeters per minute. So this is the rate at which our thickness of the iron of the coated ice will be melting at.